Welcome you all to Principles of Organic Synthesis. Presently we study organophosphorus, sulfur, silicon, boron and tin reagents. So far we had 2 lectures in this topic. In the first lecture we studied the preparation and application of organophosphorus reagents. In particular, we studied the olefin formation from using phosphorus ylides. The second lecture we studied organosulfur and silicon reagents. If you remember, in the organosulfur chemistry also we focused 3 types of reactions. First, we studied the preparation of sulfur ylides and the reaction with the carbonyl compounds, ketones and aldehydes to give epoxides. Later we also learned that these ylides can be used to react with the amines to give aciridins. If you have alpha beta unsaturated carbonyl compounds, the ylide that is formed from sulfoxynium ion can be reacted at the double bond to give the donor acceptor cyclopropane. Then we have seen the transformation of ketone to alpha beta unsaturated carbonyl compounds. For example, if you have the ketone alpha position, you can try to introduce thioether group which can be oxidized to sulfoxide, that when you heat it can undergo elimination to give alpha beta unsaturated carbonyl compound. Then we have seen the reversibility of polarity of carbonyl compounds. For example, if you have the aldehyde and ketones, you can try to react with 1,3-dithione, which can convert into dithioacetal or dithioketal, which can be readily reacted with alkyl halide. For example, if you have the dithioacetal, which can be reacted with the base to generate the anion, which the anion can be stabilized by d orbital of sulfur, that can be reacted further with alkyl halide, or you can carry out addition reaction with the carbonyl compound to give ketone or alpha hydroxy ketone as the product. It depends upon the substrate. Then we have seen some rearrangement, for example 2,3 sigma-trophy rearrangement. Then application, for example, if you have the aryl system, you can try to get the rearranged products. Following that, in the organosilicon reagents, we have seen mainly the Peterson olefination. You can try to change the stereochemistry using different reaction conditions. For example, you can use base or acid. Accordingly, you will be able to control the stereochemistry of the alkene. Then we have seen the production of alcohols. We have taken some examples. For example, we have taken the tributyl dimethyl silyl chloride, and which tertiary butyl dimethyl silyl chloride, which can be used as a protecting agent for the alcohols in the presence of imidazole as catalyst. And this is a stable and normal acidic conditions. After the reaction, you can try to cleave the silyl ether using fluoride ion. In this way it will be very useful. And we also have seen the reactivity profile of alcohol. Primary alcohol reacts much faster comparing to secondary alcohol, which reacts much faster comparing to tertiary alcohol. In this way, for example, your substrate has both primary and secondary or tertiary alcohol. You can try to product one of them. The remaining can be kept intact, which can be further reacted to get the compound. So then we also have seen the some addition reactions. You can also, we have the allyl derivative which can be carried out to the addition reaction to carbonyl compounds. Similarly, we also have seen in the case of sulfur reagents olefination. If you have the sulfone which has the alpha hydrogen, which can be reacted with lithium or magnesium, will be able to generate the anion, which can be further reacted with the aldehyde by addition reaction, followed by then you can react with acetic anhydride. Once you have the acetate, when you react with the sodium amalgam, you can replace the sulfone, and which can undergo elimination to give the alkene. Usually we get the transalkene there. And these are some of the important reactions we have seen in the last lecture. In this lecture, we will try to focus on the boron and tin reagents. Here the preparation of organoborane is shown, and if you look at the literature, this some of the boron reagents commercially available. For example, this is commercially available. When you And similarly, so these are the reagents commercially available you can use. You can also, so once we have the reagent here, the preparation of organoborane shown here, and this speciality of this reagent is that it can, the diborane can undergo addition reaction with the alkene, and you will be able to get the addition product. If the look at the reaction is regio specific. Always the boron undergoes reaction with the less substituted carbon here. For example, this substituted carbon, this boron undergoes addition here. If you write like this, so the boron approaches always the less substituted carbon, and you will be able to also syn addition. The boron and hydrogen undergoes reaction in the same phase, top phase or bottom base of the alkene. You will be able to get the addition product. And since you can have, if less sterically hindered alkene, you can try to react with 3 alkene, you will be able to get the trialkyl borane. This way you will be able to make organoborane. For example, here, and the more substituted alkene is given here. In this case, 2 molecule of alkene undergoes addition reaction, and you have the one of the BH bond is left here. So 2 molecule of alkene undergoes addition reaction, you can get this dialkyl borane. And now let us look at this one. In this case, and this borane undergoes addition, or 3 all alkenes undergoes addition, you will be able to get this alkyl borane. In this case also, this more sterically hindered one, in this case only 1 alkene undergoes addition reaction, you will be able to get this thiaxyl borane as the reagent. So if you have the borane which can be readily undergo reacted with alkene to give the addition product to get the organoborane as a reagent, which can be further utilized for the several transformations. Now let us look at here in this alkene, and if you react with the borane, and boron always approaches this side, and you can less hindered side, and 94% you can the selectivity, and you will get the corresponding addition product. Whereas you have the alkene, one side you have the bulkier substituent, another side you have the methyl group. Here also that boron undergoes the less bulkier side, it undergoes addition reaction, you will be able to get the corresponding addition product. And now let us look at this alkene, and this cyclopentene having a methyl group. In this case, this is a less substituted one, and this is a disubstituted. This boron comes to this side, therefore you will be able to get this compound. In this case, 2 molecule of this methyl cyclopentene undergoes addition reaction, you get this organoborane. As now let us look at here, and again you have the top phase, bottom phase. This the boron hydrogen undergoes addition, syn addition, therefore, and you see here the bottom side you have the methyl group, and this hydrogen, whatever it comes from the boron, it undergoes syn addition. Similarly, and you can see another one, stereo specifically you can undergo addition, the less hindered phase. And for another example here, and if you look at here, this side is less hindered, the top side compared to the bottom side, due to the steric repulsion, therefore here the boron addition reaction takes place the top side to give the organoborane derivative. So here another example, cyclooctadiene is given here. As just we have seen, this also can undergo reaction, as you will be able to get this 9-BBN, and which is this also commercially available, and which can use for the transformation. And here optically active alkene is shown, which can alba binding, which can undergo addition reaction, and you will be able to get this compound should be written like this, because the top side you have the 4-member ring, the boron approaches from the bottom side, then you will be able to get this addition product. Once if we have this one, this can be used for the asymmetric version of hydroboration oxidation reactions. Now let us just, we have seen borane can readily undergo reaction with alkene to give the organoboranes. And so we have seen the reaction stereospecific, both hydrogen and boron at the same phase of the alkene to give the addition product. And if you look at always the boron approaches less substituted carbon side to minimize the steric repulsion, you get the addition product. And depends upon the nature of the alkene, if less substituted alkene, 3 molecule of alkene can react, addition reaction, you will be able to get alkyl borane. Or if you have bulkier one, you get the less substituted alkyl borane as the product. Now let us look at this molecule here, and when you have this alkene and it can undergo, when you react with borane, you will be able to get this alkyl borane. And this borane, when you heat it at 150 degrees Celsius, it undergoes elimination followed by addition. So in other words, you can see here it undergoes isomerization, because it first it undergoes elimination followed by addition. Therefore, you get here less substituted. You can see here the terminal borane, you get it. Here the more substitute, due to steric reason, it eliminates, then it undergoes addition. Therefore, you get this as the major compound. And now let us look at the other compound here. This alkene also, the tetrasubstituted alkene here. So when you react this alkene with the borane, you get this addition product. Due to the stericness, only one alkene undergoes addition reaction, you get this. When you heat this alkene, this also can, as you can see here, convert into, it can undergo elimination followed by addition reaction. You will be able to get this borane. Once you form this one, when you do the oxidation, then you will be able to get the primary alcohol as a product. So if you have this borane, then it can be, when you heat it, you will get this one, which can be further oxidized to alcohol as the product. So far we have seen the preparation of organoboranes and then their rearrangement, isomerization. If you heat, they can undergo elimination followed by addition reaction. You get the less sterically hindered borane as the organoborane reagents. Now let us look at their application to alcohols. Already we know that, for example, if you take this example, methyl cyclohexene, when you do the oxymercuration, demercuration, this is a product which, when you treat with sodium borohydride, the presence of base can produce alcohol. So if you have this alkene, you can see here this position undergoes a reaction, then you will be able to get the tertiary alcohol in the product. On the other hand, if you want to this other regioisomer, for example, if you want this alcohol, and you can carry out this reaction using borane, and borane, as we have seen, it will undergo addition less hindered side, you will be able to get, once you form this one, this when you do the oxidation, you can convert into alcohol as a product. So if you want to make the other regioisomer, hydroboration oxidation is the best approach. And if you want to make the highly substituted one, you can use oxymercuration, demercuration, you will be able to get this alcohol. Now let us see the reaction pathway. As we have seen, when you have the alkene which can undergo reaction with borane, you get the organoborane. Once you form the organoborane, when you react with the hydrogen peroxide in the presence of base, it can convert into alcohol as the product, where you generate this as a byproduct. So if you have the organoborane which can be readily oxidized using hydrogen peroxide in the presence of base to give the alcohol as a product, the mechanism shown here, and the presence of base, the hydrogen peroxide can be converted into this, which can undergo a reaction with the borane, then you can get this can undergo reaction with the organoborane, you will get this intermediate. Once if you have this one, now this can migrate here, and then you will be able to have this. Once you form this one, this hydroxide can now react with this borane, then you will be able to so when you do the workup, it will be converted into alcohol. Similarly, all this can be converted into alcohol. For example, if we have this one, this can be converted into when you react with the hydrogen peroxide, it will be converted into this alkoxyborane. Once if you form this one, this can be, when you do the hydrolysis aqueous workup, you will be able to get the 3 molecule of alcohol. Now let us look at one application here, the reaction of this methyl cyclohexene shown here. This can be, as just mentioned, you can try to react it, then you will be able to make this alcohol as the product. You can see here, and the hydrogen and the OH group come the same side, and syn addition, then you will be able to get this alcohol as the compound. For example, if you have the chiral borane, you will be able to get the optically active alcohol as the product. Now here shown for the enantiomer selective alcohol synthesis using optically active organoborane reagent, and for example, if you have the alkene, you can try to react with this optically active borane, you can undergo addition reaction, you have the optically active organoborane, once which when you do the oxidation, as you can see here, and you will be able to get the compound. Here whatever the chirality you have, this is retained in the molecule, you can see here. Just it migrates when you react with so when you react the hydrogen peroxide and sodium hydroxide, and just you can form so you can see here the chirality is retained in this, and with the retention configuration it will be so when you do the hydrolysis, it will be converted into product. Similarly, if you take this trans alkene, which can undergo reaction similar way, then you will be able to get the opposite enantiomer. So both enantiomers can be prepared. For example, you can take the two different alkene. If you take the cis alkene, you get this. If you take the trans alkene, you get this other enantiomer, and you can also use opposite enantiomer of the organoborane reagent, which can give the corresponding the opposite enantiomer when you do the oxidation. And here an example shown, the transformation into primary amines. You have the organoborane. So when you react with this amine, you can, when you have the X, can be Cl or sulfonic acid. So when you react, so you will be able to, it can undergo addition reaction as shown here. Once then this R group migrates, then you will be able to get this intermediate. Once we have this intermediate, now this can be, when you do the aqueous workup, you will be able to get the primary amine as a product, where you generate the boron hydroxide as a byproduct. Now let us look at the carbonylation of organoborane. So far we have seen some examples where you can react a chiral borane, for example optically active borane, you can try to react with alkene, so you can get the corresponding optically active organoborane, which once you generate, which can be oxidized using hydrogen peroxide to give the optically active alcohol as the product. Now let us look at the transformation into tertiary alcohol. If you have the carbon monoxide, which can readily undergo reaction with borane and to give the tertiary alcohol as a product, the condition shown here. The mechanism of this transformation shown here, which can now undergo reaction, then you will be able to get this adduct. Once you form this one, now this can undergo migration, then you will be able to get this derivative, carbonyl derivative. Once if you have this one, this reaction usually carried out in ethylene glycol. Once if you have this one, now this can, and you will be able to have this intermediate. Once if you have this intermediate, this can further react, and you will be able to form this. Then it can further react with another molecule of ethylene glycol and migration, then you will be able to get this borane derivative. Once you form this one, when you do the oxidation, then you will be able to have tertiary alcohol as the product in this reaction. So if you have the carbon monoxide and you can convert into tertiary alcohol as the product, this is how you can carry out this reaction carried out under heating in ethylene glycol. Now let us look at the formation of ketone and secondary alcohol. Just we have seen, if you have the organoborane, which can be reacted with the carbon monoxide, that can lead to tertiary alcohol as a product. Here the formation of ketone and secondary alcohol shown, and if you have, when you carry out the reaction in the presence of water, you will be able to stop here. Once you form this one, now this we can undergo oxidation, the presence of hydrogen peroxide in aqueous medium, and the presence of base, it can undergo oxidation with hydrogen peroxide to give ketone as a product. On the other hand, you can also do hydrolysis that can lead to the formation of secondary alcohol as a product. Here another example shown, when you take this thiaxyl borane, which can undergo, you can try to react with the two different alkene, and you will be able to get this compound. Once you form this one, this can be further reacted with the carbon monoxide in water medium, then you will be able to get ketone as a product. So in the presence of hydrogen peroxide and sodium hydroxide, you can also, for example, you can couple two alkene, and an example shown here, this diene can be reacted with the thiaxyl borane as just we have seen, then you can form this bicyclic system. Once you form this one, now it can undergo reaction with the carbon monoxide and water, and then when you do the oxidation using hydrogen peroxide in the presence of sodium hydroxide, that can lead to the formation of the bicyclic ketone as a product. Now let us look at here, since the borane and the hydrogen comes on the same side, syn addition takes place. You can see this comes from the borane, and it should be blue color. It comes same side, syn addition takes place, and once the addition takes place, then it can react with another, then you will be able to get this 5-membered borane reagent. Once you form this one, this can be further react with carbon monoxide in the presence of water, and you can further oxidize the intermediate with the hydrogen peroxide in the presence of sodium hydroxide to give this bicyclic ketone as the product. Here an example shown, you can also, once you form the intermediate, that intermediate can be reacted with here trimethoxy lithium aluminum hydride is shown here, which can readily undergo addition reaction with the carbonyl group, and you will be able to have this intermediate, which can be oxidized to aldehyde as a product. So if you have the intermediate, this can be readily reacted with the trimethoxy lithium aluminum hydride to give aluminum alkoxide. Once you have this one, which when you oxidize, it can be converted into aldehyde as the product. Here the reaction with the cyanide ion shown here, which can also undergo reaction, and you will be able to have this intermediate. And this is similar to the carbon monoxide just we have seen, and similarly it can also undergo reaction here, then you will be able to have this intermediate. Once if you have this one, when you react with this anhydride, can undergo addition reaction, you will be able to have this amide derivative. Once if you have this, you can try to react with the anhydride, you will be able to have this derivative. Once if you have this one, which can now undergo migration as shown here, and you will be able to have this intermediate that can lead to cyclization to give this heterocyclic scaffold, which in the presence of hydrogen peroxide and sodium hydroxide can be converted into ketone as the product. So, if you have the nitrile, and which can be readily reacted with borane in the presence of trifluoroacetic anhydride to give ketone as a product, and similarly if you have this intermediate also can be further reacted with the trifluoroacetic anhydride further, excess trifluoroacetic anhydride, then you will be able to get this adduct. Once you form this one, which can now rearranges as shown here, and you will be able to get this derivative, which can undergo oxidation to give tertiary alcohol as the product. So, if you have cyanide ion, that also can be reacted with the borane, that in the presence of excess trifluoroacetic anhydride can be converted into tertiary alcohol as the product. So, it depends upon the reaction conditions, you can convert into ketone or secondary alcohol or primary alcohol as the product. Now, let us look at the formation of ester. Let us look at this alpha halo ester. Once if you have this one, when you react with sodium tertiary butoxide, which can deprotonate this one, you will be able to form the enolate. Once you form the enolate, which can undergo reaction with the borane, and you get this intermediate. Once this can now convert into this alkyl borane by removal of Br minus by a substitution reaction, you will have this intermediate. Once we have this one, this can undergo tautomerization as shown here. This, when you do the hydrolysis, you will be able to convert into ester as the product. In this case, and this Br has been replaced with the alkyl group, and as you can see here, you can try to react as shown here. Then once you can, so this the R can migrate here, and Br leaves via SN2 pathway, and once you form this one, which when you do the hydrolysis, you will be able to get this ester as the product. Now, let us look at here the reaction of alkyne with 9-BBN. Just in the beginning we have seen, if you have the cyclooctadiene, you can try to react with the borane, and you will be able to make 9-BBN, and this can readily undergo reaction. It is a bulkier reagent, and syn addition you will be able to get this vinyl borane. Once we have the vinyl borane, now you can try to oxidize, you can convert into OH group. So, this can now convert into ketone as a compound. So, if you have the alkyne, you can try to react with the borane, and when you do the oxidation, you will be able to convert into ketone as a product. On the other hand, if you have the terminal alkyne, you can carry out the reaction similar way. The borane comes to the less substituted side. Now, you can try to oxidize, then you get the corresponding aldehyde as the compound. So, if you have the hydrogen in this case, when you do the oxidation, you can convert, if you have the terminal alkyne, you can convert into aldehyde as a product using by hydroboration oxidation. Now, let us look at the synthesis of alkenes. Here the reaction of the terminal alkyne with organolithium shown, and this can act as a base. A deprotonation can lead to the formation of alkynyl lithium reagent. Once you form this one, when you react with Br2, and you can make this bromo derivative, which can now undergo addition reaction with borane, and you will be able to get this addition product. This should be blue color, and once you form this vinyl borane, now this, when you react with methoxide, it can undergo reaction with this borane, then you can generate this intermediate. Once you have this one, this can now migrate here and this can leave, and you will be able to have this intermediate. Once you have this one, when you treat with acid and you can replace in this way, you will be able to get this alkene as the compound. So if you have terminal alkyne as shown here, you can try to react with the base and you can introduce the halogen here. Once you have introduced the halogen, is a good leaving group, and you can react with your borane, and you get this vinyl borane derivative, which can, when you react with methoxide like this, it can react with the borane, then this is negative charges here. Now this R group can migrate here and Br leaves, and you will be able to get this vinyl borane derivative, which when you do treat with acid, and you will be able to convert into trans alkene as the product. Here an example shown, and the reaction of this alkyne with borane, it can undergo addition reaction as just we have seen, and the borane comes in the less hindered side here, and you get this additional product. Now when you react with hydroxide ion, just as we have seen, it react with borane, you get this intermediate. When you react with iodine, you generate this iodine intermediate. It can, the R prime can migrate here and it can open up, and you will be able to get this iodo derivative. Once if you have the iodo derivative, when you react with hydroxide ion, it can further react with this borane, you will have this reagent. Once if you have this one, now this can undergo elimination to give alkene as the product. Here the formation of conjugated diene shown. When you react with this alkyne with the texyl borane, and you will be able to get the addition product as we have seen. This should be a blue color, syn addition. Once if you have this one, it can also undergo further reaction. Since you have one more hydrogen, it can undergo addition reaction. You will be able to get this addition product. So now do different alkynes shown here. Here you have the substituted alkyne. Here you have the terminal alkyne. They can undergo addition reaction. Then you will be able to get this compound. Now you can try to react with the sodium methoxide, and it can react here, and you will be able to form, once this one, this, then one of them can migrate as shown here. It can undergo reaction here, this can leave, then you will be able to get this intermediate. And this, once you have this one, when you react with the acid, then you will be able to get the diene as the product. So if you have the alkyne, you can, two alkyne can be coupled into give the diene as the product using this reagent. The next example shown here, the reaction of internal alkyne shown. When you react with the catechol borane, so you can undergo addition reaction as just we have seen, and then you will be able to get this addition product, organoborane. Once we have this one, as we have seen the earlier, you can try to react with bromine, and you will be able to get anti-addition product. Once if we have this one, now this can, when you react with the base, and it can undergo reaction that can lead to elimination, you get this compound. This similar to the previous case we have seen here. When you have this one, this can leave here, then you will be able to get alkene as a product. Similarly, in this case, once we form this intermediate, that can undergo elimination to give alkene as the product. So far we have seen the preparation as well as the reaction of organoborane reagents. Now let us look at the recent development in the boron chemistry, and here an example shown. And when you hear this CH bond has been coupled with this boronic acid using transmetal catalysis, and this you can, in this way you will be able to introduce here aryl group in this case, and the oxygen insertion takes place, and in this way you will be able to get the diaryl ether. Basically what you have to here remember, the recent development, even if you have the organoborane like this, boronic acid can be coupled, and in this way using the tungsten metal catalysis via CH activation, and this is a very important reaction as you can see here. And the many of the biologically active compound, for example this molecule has this moiety, so therefore if you have the boronic acid you can try to couple, you can make this compound. Similarly this also, if you have the, you can make with the boronic acid, once you make this one then you can make a bond via CC bond formation. So this now recently much progress has been made in the boron chemistry. For example, you can try to couple the boronic acid via CH activation, you can make the diaryl ether as a product, and the mechanism of this reaction shows, and then we have carried out the kinetic isotope studies as shown here, and then found that when we carry out the reaction with the boronic acid and using here you have a mixture of, one has a deuterium, another was simple compound. When you take a mixture of 1:1 with a deuterated compound, when you carry out the reaction, and there is a, the observed unreacted compound found is about almost, you can see here 1:2, which shows that the KH by KD 1.94, which suggests that the CH bond cleavage may be the slow step in these reactions. Then also when we carried out the source of oxygen, found the oxygen comes from the water molecule. When we carried out the reaction in the presence of labeled water, it found that the oxygen incorporation takes place from the water, and this, based on that, the mechanism has been proposed. And what may happen here, you have the copper to acetate in the presence of base can react, then you will be able to form this copper to intermediate. Once you form this one, which can be further converted into a copper 3 by redox process, and here the copper 2 is reduced to copper 1. Once you form this one, and this can now activate the CH bond, and you will be able to form this copper 3 intermediate. Once you have this one, this can be reacted from the phenol that you generate from the boronic acid and water in the presence of CC carbonate as shown here, and you will be able to form this intermediate. Once you form this one, this can give the product by reduct elimination, and you can see here the boronic acid in this reaction is converted into phenol that further undergoes reaction with this intermediate, and you remove the acetic acid, you have this copper 3 intermediate that can give the product by reduct elimination to complete the catalyst cycle. Another example is here shown, the reaction of boronic acid with this indolene moiety. This 7CH bond has been selectively reacted. In this the CC coupling takes place using this combination of cobalt and manganese acetate in the presence of phosphine ligand in HFIP solvent. The combination of this reaction condition is crucial for the transformation. This also very important reaction, as you can see here, indole having aryl group in the 7th position shows very interesting biological properties, and similarly for another molecule you have the indolene and you have the aryl group, and therefore the coupling of boronic acid with this substrate will be very useful. And here the reaction in the presence of radical scavenger like tempo and less effective, and that means the reaction may involve a radical intermediate. Already if another one radical is involved, when you add another radical, the reaction can be slowed. This is what happens here. So this, the drop in the yield clearly shows that the reaction involves a radical intermediate. Then also, as just we have seen, kinetic experiment using a mixture of deuterium and undreiterated compound have been carried out 1:1 and found KH by KD 1. This result clearly shows that the CH bond K may not be involved in the rate determining step. So based on that, the following reaction mechanism has been proposed. In this reaction, the cobalt 2 may be oxidized to cobalt 3 by manganese 3, where manganese 3 is reduced to manganese 2. This can be further oxidized to manganese 3 by oxygen. Once if you have the cobalt 3, which can make chelation with this nitrogen 1 pair, activate the CH bond, and you make this intermediate. Once if you have the intermediate, now the boronic acid with manganese 3 can convert into phenyl radical, and manganese 3 is reduced to manganese 2, and manganese 2 whatever you reduced, it can be oxidized as just we have seen by oxygen to manganese 3. And once if you see form the phenyl radical, the phenyl radical can react with this cobalt and we make this intermediate cobalt 4. Once you have the cobalt 4, this can give the product by reductive elimination and you regenerate the cobalt 2 as the catalyst. As you can see here, the boronic acid can be readily coupled with aromatic systems via CH activation using transition metal catalysis. We have seen two examples. First one involves a copper based system, and second one involves a combination of cobalt and manganese system, which can be used to couple if you have the indolin, and it can be functionalized with the boronic acid via you can do the arylation reaction. Now let us look at here. Already we have seen the Susi coupling reaction. So this also you can see this is very important transformation. Already we have discussed in the earlier lecture, all of you know very well. If you have, for example, aryl halide, for example aryl bromide, if you have the boronic acid, in the presence of palladium 0, let us take sodium tertiary butoxide. When you try to react this aryl halide with boronic acid, you can do CC coupling and you will be able to form the biaryl system. Already we have seen detailed the mechanism. If you try to remember, the palladium 0 undergoes oxidative addition with your aryl bromide, you have this addition product. Once if you have this one, this can react with the sodium tertiary butoxide once if you have this one, this can undergo reaction you form this salt. Once you form this one, this can now undergo reaction here and you will be able to form so this can give the product by reductive elimination. See, if you try to remember here, first the palladium 0 undergoes oxidative addition here. So you have the palladium 2 intermediate which can undergo reaction with the base, and you will get this sodium tertiary butoxide. You will be able to get this palladium 2 intermediate. Once if you have this one, this can react with the 8 complex you generate from boronic acid and sodium tetrahydroxide. This is a crucial step. Once you form this one, this can react, then you will be able to form this palladium 2 intermediate, and this can give the product by reductive elimination to complete the catalyst cycle. This reaction has been well explored, and if you remember in one of the class we have studied in detail. So if you can see here, these are some of the recent developments. In addition to that, there is also much reports available. The coupling of boronic acid for example, you can try to couple with aniline and phenol. For example, if you couple with aniline in the presence of copper, you can make this CN coupling product. And similarly, on the other hand, if you take phenol, this also you can try to react. These are some of the recent developments. You can use the boronic acid for cross coupling reactions. In this way, you can make alkyl or biaryl systems, alkyl aryl systems. You can also try to couple with the phenol, aniline, thiophenol. You can construct a carbon heteroatom bond, and you will be able to get very useful compounds. You can also try to react boronic acid for the CH functionalization. In this way, here on example shown, you can do the CC bond formation. In other words, you can do the arylation, which is very useful reaction. The combination of cobalt, manganese has been shown here that can catalyze the reaction. Then you will be able to couple the boronic acid. You can get this compound. And the previous case we have seen, you can also try to react boronic acid for CH functionalization using copper based systems. You can make diaryl ether as a product. Now let us look at the organotin reagents. If you look at the organosilicon, so organotin reagents more reactive, and if you look at the bond, this one silicon, this is longer and is polarized, easily you can react. And however, this toxicity of tin limits its potential applications. We will see some of the important transformations in this topic. Here the Stille coupling shown. This is also very important transformation. For example, if you have the aryl halide and if you have the tributyl tin derivative, it can be aryl or alkyl group as shown here. And when you have this one, this can be here shown. It can be vinyl tin or allyl tin, or you can alkynyl tin or aryl tin. You can have different substituents. They can be readily coupled. This can be, suppose here the allyl halide is shown here and benzyl halide, and you have aryl halide. They can be readily coupled with this organotin reagent. In the presence of palladium catalyst, you will be able to get the CC coupled product, where you generate this as a byproduct. And this is the mechanism of this reaction shown as just we have seen the SUSI coupling, and here also palladium 0 is involved, and which can undergo addition reaction with this halo substrate, whether it can be allyl halide or benzyl halide or aryl halide. Once it can undergo oxidative addition, you get the palladium 2 intermediate. Once you have the palladium 2 intermediate, you have the organotin reagent, and this R prime undergoes a reaction here via transmetallation, and you will be able to get the tin halide as the byproduct. Once you form this one, this can undergo isomerization, and then you get this. This can give the product by reductive elimination to complete the catalyst cycle, and this reaction has also been well explored. And however, as I just mentioned, the toxicity of tin as well as the compound is less polar, it moves freely in the solvent, therefore these are the drawbacks. However, this can be used for the coupling reactions. Here the reaction of allyl tin shown as this can be readily reacted with aldehyde, and you can get the CC coupled product and addition product, and you can see here the stereochemistry. You can try to explain this reaction can be carried out in the presence of tin chloride, dichloromethane solvent at room temperature. You can get this syn diol in high yield. Here the mechanism of this transform is shown. When you have this one, this can undergo reaction, and you will be able to get this intermediate. Once if you have this one, now this can undergo addition reaction, aldehyde as shown, and it can make chelation with the to transition state. Once we have this one, this can undergo addition reaction, and then you will be able to get this reagent. When you do the hydrolysis, you will be able to get the syn diol as the product. Similarly, the case of borane also, just we have seen you can carry out the reaction. For example, if you have the borane reagent, allyl borane, you have the allyl borane, which also if you have the aldehyde, for example, similarly can be reacted. When you do the workup, you will be able to get the allylic alcohol as a product. Suppose if you use the optically active borane reagent, you will be able to get the optically active alcohol as a product. Similarly, here also you can use chiral ligand, and you will be able to get this diol with optically pure form. This reaction has been well explored. You can try to check the recent literature, and this can be prepared in optically pure form using like bienol based ligands. And some of the recent literature shown here, this organotin compound has been reacted with this halo substrate in the presence of copper 1 halide to give this substituted compound. Here the electrophile replaces the tertiary tin and with the retention configuration, and you can see here the mechanism of this reaction shown. So when you react with the copper 1 halide, it undergoes transmetallation, and you will be able to get this intermediate. Once we have this one, this can undergo reaction with this electrophile as shown, then you will be able to introduce substitution here. Here another example shown, the photocovalent cleavage of carbon tin bond via single electron transfer process, and this substrate when you react with the HBr under irradiation, and it can convert into oxidize into aldehyde and carboxylic acid, and the mechanism shown. When you have the bromine HBr, the presence of light and oxygen converted into Br2, HBr is converted into Br2. Once we have this Br2, and this in the presence of light can undergo homolytic cleavage to give the Br radical. This Br radical, when you react with the substrate, the benzyl tin derivative, organotin derivative, which can be oxidized into cation radical intermediate, where Br dot is reduced to Br minus, which can be further oxidized to bromine by oxygen, and once we have this one, this can undergo cleavage to give benzyl radical. This benzyl radical can, in the presence of oxygen, can undergo oxidation to benzaldehyde, which can be further oxidized to carboxylic acid. So these are some of the recent reports where you can see here the benzyl tin substrate shown here, which can be readily converted into benzaldehyde by oxidative cleavage of the carbon tin bond via single electron transfer process, and in this way you will be able to make the benzaldehyde, which can also be further converted into benzoic acid as the product. In summary, so in this lecture we have seen the preparation of organoborane. If you have the alkene which can stereospecifically can react with borane via syn addition, the borane as well as the hydrogen undergoes addition to the same phase of the alkene, you will be able to generate the organoborane. Then we have seen the oxidation of organoborane to alcohol. If you have the organoborane which can readily undergo oxidation to alcohol in the presence of hydrogen peroxide and sodium hydroxide, you can make primary alcohol. And we also have seen you can also try to convert into tertiary alcohol in the presence of carbon monoxide. We have seen some examples, and you can, depends upon the reaction conditions, you can also convert into aldehyde and secondary alcohol, ketone. We have seen several examples. Then we have seen the reaction with alkyne. The organoborane, not only it can undergo addition to alkene, it can also undergo addition to alkyne. Once you have the vinyl borane, that you can try to oxidize into aldehyde or ketone, depends upon the substituent. For example, if you have the internal alkyne, you will convert into ketone as the product. On the other hand, if you have the terminal alkyne, you can convert into aldehyde as the product. We have seen some examples. Then we have seen briefly the cross coupling reaction. Already we have studied the Susi coupling, the earlier reaction. If you have the boronic acid which can be readily reacted with the aryl halides in the presence of palladium 0 and base to give the CC cross coupled product. And we have seen one example. If you, for example, if you have aryl bromide, you can try to couple with boronic acid using palladium tetrahydrous triphenylphosphine palladium as catalyst. In the presence of sodium tertiary butoxide, you will be able to make the biaryl system. And then we have seen the recent development, the coupling of boronic acid. You can also couple boronic acid via CH functionalization using Thomson metal catalysis. We have seen two examples. One example using the copper based system where you can convert, you can couple boronic acid with the aromatic CH bond via CH functionalization. We also have seen one more example. If you have the indolin, you can also try to selectively functionalize the 7CH bond with the boronic acid using the combination of cobalt and manganese based systems. The later reaction involves a radical pathway. Then also we have seen some examples for cross coupling reaction. For example, if you have the boronic acid, you can also try to couple with aniline, phenol, thiophenol via carbon heteroatom bond formation using copper based catalyst. And copper and palladium based catalysts have been well explored, and in this way you will be able to make carbon heteroatom bond formation, which is very important in synthetic chemistry. Then we have seen the cross coupling reactions for the organotin reagent, Stille coupling. If you have the organotin reagent, that also can be coupled with aryl halide, for example, using palladium based catalyst system, you can try to couple. In this way you will be able to get the biaryl system, or you can construct a CC bond formation. Then we have seen the reaction of allyl tin. We have the allyl tin in the presence of Lewis acid, which can readily undergo reaction with aldehyde and ketone. You will be able to get the corresponding addition product, alcohol as the product. This reaction has been well explored. Even asymmetric version of this reaction has been shown using bienol based ligands. And similarly, you can also, if you have the allyl borane, that also can be reacted with the aldehyde and ketone, you will be able to get the addition product. And then we have seen the you can also try to couple with alkyl halide. Instead of aldehyde, you can also coupled with alkyl halide, you can make the CC bond formation. See, these are some of the recent reactions in the organoborane, organotin reagents. As you can see here, we have seen several reactions using organophosphorus, organosulfur, organosilicon, organoboron and organotin reagent. As you can see here, they have broad applications which in synthetic chemistry to make variety of functionalized molecules. With this, we conclude this lecture. Thank you very much.